So our goal on week 4 here is to continue pressing, continue trying to find better and better conditions that are equivalent to a square-free natural number n being the area of a right triangle with rational side lengths. Let's very briefly touch up on what we talked about last time. We built the zeta function of an elliptic curve, and really all that is an object that sort of encompasses all the information you really need to know about the number of the solutions to your elliptic curve over any given finite field that's a power of a certain, whose size is a power of a certain prime number. And we saw, for example, that our congruent number elliptic curves, which you may recall are given by y squared equals x cubed minus n squared x, they have the following zeta functions for any prime p that does not divide 2n. The zeta functions look like this. So they look like 1 minus 2 times this constant that only really depends on n and p times t plus pt squared over 1 minus t times 1 minus pt. And we have all the information we need to know about what this constant a and p actually is. Okay. And that really just depends on whether or not p is 3 or 1 mod 4. Then we began to wonder, is there a way to take all of these zeta functions, because the problem with the zeta functions is they really only encompass information about solutions over fp to the r where p is a fixed prime. Is there a way to build one function that tells us everything we need to know, sort of, about all of the solutions over all finite fields for our elliptic curve? And the model case we looked at was the Riemann zeta function. And we saw that the Riemann zeta function extends analytically onto C, except that it has a simple pole at s equals 1 with residue 1. And just as importantly, the Riemann zeta function has this nice functional equation. Okay. So what we're looking for in our personal function that we're going to build for our elliptic curves is a function that maybe is defined as a series like the Riemann zeta function is, but maybe it extends analytically onto C, and it has a nice functional equation. So those are the two things we want. Those are the two things we gather from the Riemann zeta function toy case, and we want those to be true for our function. So that in mind, we took our congruent number elliptic curves, E sub n, and we defined the so-called L function for the elliptic curve. And you can do this for any elliptic curve, of course, but we only really care about our congruent number elliptic curves. And here's what we did. We took all the zeta functions, allowing p to vary over all primes of good reduction, and we made a substitution. See, in the original zeta function, it's a function of a complex variable t. We replaced t by p to the negative s, where s is a complex variable, so that we would end up with a nice Euler product type formula like we get up here with the zeta function right here. We were motivated by this formula for the zeta function to introduce that substitution. And if you go back to the zeta function, this is something I didn't emphasize as much last time as I wish I would have, but if you go back up to the zeta function, what do you actually care about here, right? You don't really care about these two terms down here as much. They don't contain, the crucial information here is this a sub np, right? And so that's why in the definition of the L function, using the Euler product of the zeta function, the Riemann zeta function, if you take this product you formed of all the zeta functions and you divide the Riemann zeta function at s times the Riemann zeta function at s minus 1 divided by this product, what ends up happening because of the Euler product formula for the Riemann zeta function is you basically get rid of all this stuff here that you don't care about in the denominator. And you're left with the crucial information, the piece of the fraction that's got this constant in it that we really care about. So that's why this numerator was introduced here. And you can show that easily. I mean, here's a nice expression for the L function. It's an infinite product over all primes of good reduction, meaning primes that don't divide 2n, of this nice simple little rational function here. Well, exponential function. I think that's about where we stopped. And one last thing I want to just kind of review or recall is, where are we? What's the current state of the congruent number problem? The current state is we know the following. A square-free natural number n is congruent if and only if the rank of, where is it? Right here. A square-free positive integer n is congruent if and only if enq, which remember is the group of all rational solutions to en, has non-zero rank. If you like, thanks to the structure theorem for finitely generated abelian groups, what you can really think of this as is a natural number is congruent if and only if there are infinitely many rational solutions. Okay, which I think I even wrote somewhere. Right here, yeah. Square-free natural number n is congruent if and only if enq is infinite. There are infinitely many rational solutions. Of course, while this is very profound, it's still not checkable, so we would like to continue to push further. And today we're going to really get to the peak of all this. We're going to probably be ending the elliptic curve side of things today, which means, roughly speaking, we're going to be something like halfway through the argument, hopefully by the end of today. And the rest of the talks will be on modular forms because we're going to have to utilize those to keep going. Okay, so we've got our L function here. Now, the L function is a nice product over primes. If you actually expand this product out, you're going to get an infinite sum, of course. And it's going to look something like this. It's going to look like a Dirichlet series, meaning it's going to be some infinite sum of some coefficients that depend only on the index m and, you know, the number n whose congruent number curve we're looking at, times m to the negative s, where again, s is just some complex variable. So you expand this out, you get this. There's nothing, there's no work there. And then what's the natural question? The natural question is, what are these coefficients, right? What are those? How do you compute them? Do we know how to compute them? Do they tell us anything profound? But more secretly, are these coefficients, do they come from somewhere else? Will we be able to realize these coefficients as coming from another world, so to speak? And the answer is yes, but we won't see that for a little while. There are more pressing immediate questions than this, though. Like, this is an infinite series, right? When does it even converge? So I'll leave it to you to check. It's like 2 or 3 lines. You can show this converges as long as real part of S is bigger than 3/2, right? So we at least on our right half plane and the complex plane, we're at least converging. So we're something like this. So here's the complex plane, blah, blah, blah. Here's 1, here's 2. We're at least convergent to the right of this. Kind of like how the Riemann zeta function was only defined for real part of S bigger than 1. But remember, what were we able to do with the Riemann zeta function? We were able to extend it to the whole complex plane except for just one little pole. What will happen in this case? I don't know. We'll find out soon. Very crucial observation coming up. Let's say remember how last time I was talking about if you knew the number of FQ solutions to an elliptic curve, there was a way to produce the number of FQ to the R solutions for any R. I briefly touched on this last time. In the same way, we kind of wonder the following. Let's say I have L of E sub 1 of S. In other words, I have all these coefficients when n is 1. Is there some way of finding these coefficients when n is bigger than 1? Just by knowing them when n equals 1? You might guess that surely there's no way this is possible, but in fact it is. Before I state the result, I need to tell you something though. So recall last time we defined the Legendre symbol, and it was defined more or less in the following way. A over P is how it's written, and it's 1 if A is a square mod P and -1 otherwise. But the thing was, in our original definition, P had to be a prime. It turns out it's very easy to extend this function multiplicatively in P in the following way. So let's say D is an odd positive integer. I can actually look at the Legendre symbol of C over D for any C, even though D is not necessarily prime. And the way you do that is you just extend this function multiplicatively in P. So for example, if D is like P1, P2, okay, then C over D would be by definition C over P1 times C over P2. Okay, that's if D is an odd positive integer. If D is negative and odd, then what you do is you define C over D, the Legendre symbol, to just be C over the absolute value of D, if C is positive. And negative Legendre symbol of C over absolute value of D, if C is negative. And then there's a kind of a pathological thing that comes up. What happens if you do the Legendre symbol of 0 over plus or minus 1? You want to just define that to be 1. When you do that, you get a nice function with nice multiplicative and periodic properties. We don't really need to get into that. But here's the thing that you're going to do with this newly extended Legendre symbol. You're going to make a multiplicative character out of it. So what does that mean? A multiplicative character is just a multiplicative homomorphism from a group to some multiplicative group of units. Okay. And so what I'm going to do is I'm going to define a character from the integers to the units of C. And here's what it's going to do. I'm going to send an integer to the Legendre symbol n over m. Now I have to put some requirements on m here, because remember, this is only actually defined if m is odd. Not only that, but I don't really want m to divide n, right? Because in that case, the Legendre symbol is defined to be 0. That's kind of a stupid case nobody cares about. So I'm going to impose the extra restriction that the greatest common divisor of m and 2n is 1. And that resolves both of those issues at once. And you can check very easily here that you get a multiplicative character. And so who cares? So we've got a nice beefed up Legendre symbol here. What do we do with this? So here's the theorem. Let's suppose I already know the L function of E1, and it's given by this infinite sum here. The sum from 1 to infinity, B, we'll call B sub m the coefficients in this case, times m to the negative s. So suppose I already know this. Then it turns out the L function of any congruent number elliptic curve is basically the same sum, but all you have to do is so-called twist these Bm by the character chi sub n. You just have to multiply them by this Legendre symbol. That's it. And this is huge. We will need this later once we learn enough about modular forms. This is going to be like, if this is kind of a linchpin, if I'm being honest. If this wasn't true, we might be in some serious trouble here. So this thing that you're doing right here is called twisting the coefficients by a multiplicative character, or twisting the coefficients by chi sub n. Okay. And so that's great. So we've kind of addressed two issues right off the bat. Does our L function ever converge? Yes, it converges on our right half plane. And then do we continue this trend of once we know things about n equals 1, do we know things about bigger values of n automatically? And the answer is yes. But what were the really pressing questions? The really pressing questions were, does our L function analytically continue, and does it have a functional equation? And so theorem, big theorem. Analytic continuation of the L function. It turns out you actually get a little bit better of an analytic continuation than you do with the Riemann zeta function. L of En of S and S extends analytically to an entire function. There are no poles anywhere. Okay, so that's the first thing. Second of all, you do get a functional equation, and it's pretty nice. If you let capital N be 32n squared, if n is odd, little n is odd, and 16n squared if little n is even, and then you define lambda to be the following: square root of n over 2 pi to the s times the gamma function evaluated at s times your L function evaluated at s. Then lambda satisfies this functional equation. Lambda of s equals plus or minus lambda of 2 minus s. So some differences here between this and the Riemann-Zeta functional equation. First of all, there's this plus or minus here. What's going on there? Second of all, in the for the Riemann-Zeta functional equation, this 2 was a 1, which is no big deal at all. It's just worth pointing out. But as a matter of fact, we know exactly when this is plus or minus. It's plus when n is 1, 2, or 3 mod 8, and it's minus if n is 5, 6, or 7 mod 8. And if you're wondering why I didn't say 0 or 4 mod 8, think about it and don't think too hard. Okay, so this is exactly what we were hoping for, right? In fact, it's almost in some sense better than what we were hoping for. We extended to an entire function. We didn't have any singularities afterward, no poles, nothing. And we did sacrifice a little bit with the functional equation, but the sacrifice we made, the extra complexity we added in, is well understood. Okay. Now, what do you notice about this functional equation? You notice that s equals 1 is the so-called fixed point, right? Or the critical value. If I plug in 1 into both sides, I get lambda of 1 on both sides. So that's going to be important coming up here. So this is like the critical value. In other words, it's the center of the critical strip, which runs from 0 to real part equals 2 in this case. Okay, so what have we done? We've built ourselves a nice entire function with a nice functional equation that we can attach to our elliptic curve, any congruent number elliptic curve that we want. And what is this function doing? It's somehow nicely encompassing all the information we want about the zeros of En over all of the relevant finite fields at once. And by relevant, I mean whose cardinality is the power of a prime of good reduction. Okay. So who cares? Well, now we're going to get into some heavy stuff. If you remember last time, I told you, or actually not even just last time, but also week 1 of this series of talks, I told you that there is a weak version of the Bsd conjecture that does kind of hamper our argument along the way to the proof of the congruent number theorem. And that's going to happen right now. That step comes up right now. Everything I've said so far is well known. Sunil says the sign in the functional equation is fascinating in the general case. Yeah, you mean for general L functions? Yeah, but I've seen a little bit about that. It's wild stuff. Let's summarize what we know so far. Y squared equals x cubed minus n squared x. That's an elliptic curve over any field as long as the characteristic of the field does not divide 2n. In particular, this right-hand side cubic here has 3 distinct roots, which we saw is the same thing as it being smooth. Okay. We also know so far that a square-free positive integer n is congruent if and only if it has En, that elliptic curve, has infinitely many rational points. We built zeta functions to encapsulate all the f q to the r points for each q, a power of a prime p not dividing 2n. And we found a nice rational function formula for all of our zeta functions. That was last time. We took all the p zeta functions and threw them into a big Euler product, which gave us the L function for En, which extends to an entire function and has a nice functional equation. But, you know, we've done quite a bit of work with these zeta functions and L functions. But if you look at our last characterization of congruency or congruence, where are the L functions and the zeta functions? They're nowhere to be found. We have yet to characterize the congruence of n in terms of the L function. And to do so requires the weak Bsd conjecture. And here's what the conjecture says. Let E be any elliptic curve over Q. Then E has infinitely many Q points, if and only if L of E1 is 0. So we have to internalize this. First of all, what is L of E1? What is this? Remember, L functions are only defined to the right half of real part equals 3/2. How do you know L of E1 even exists? Well, we do for our elliptic curves, right? Because we have analytic continuation. But in general, do you know this? Do you know that you can always extend any L function of any elliptic curve? Well, we didn't for a long time. But what we did know was that every so-called modular elliptic curve, and we'll see what that means later, had an analytic continuation with a nice functional equation. But thanks to Wiles, Taylor, Brule, and Diamond, and the modularity theorem, the theorem that led to the proof of Fermat's last theorem, we now know that every elliptic curve over Q is one of these modular elliptic curves. So that means every single elliptic curve over Q has an analytic continuation. So L of E1 always makes sense. So asking whether or not L of E1 is 0 makes sense now. We know this. Okay. The second thing to bring up is, why is this called the weak Bsd conjecture? The full Bsd conjecture is more specific. It says that the order of the root at 1 here is the rank of the elliptic curve. That R value from earlier that showed up in the decomposition, which is like way up here. The order of the 0 at 1 is this rank here. That's what the full Bsd conjecture says. We do not need that to be true to get the congruent number theorem. So it's worth pointing that out. What else should we point out? Not only do we only need a weak version of the Bsd conjecture to be true, we only need it to be true for our specific elliptic curves, E sub n. We don't even need it to be true for all elliptic curves. And if you would like, I'm going to give you a little summary here of what we know right now about the Bsd conjecture. First of all, there is overwhelming computational evidence that the Bsd conjecture is true in general. Overwhelming. A simple Google search will show you this. What's the most recent, most powerful theorem? Bhargava and Shankar in 2015. What they showed is that a positive proportion of all elliptic curves satisfy Bsd. And I watched Bhargava's recent Abel Prize lecture. It was actually Wiles' Abel Prize, but many other speakers gave lectures, and he was one of them. And what he said is, if you take this result that he and Shankar proved, and you combine it with every single other partial result that's known on the Bsd conjecture, then statistically speaking, we now know that more than 66% of all elliptic curves satisfy Bsd, which is huge. But then he made a joke, and I'm going to make the same joke. It's $1 million problem, the Bsd conjecture. He made the joke that no, he does not win $660,000. And I'm going to repeat that joke right now because it's funny. But more importantly, let's say we even knew 100% of elliptic curves satisfied Bsd. We still wouldn't be done. The problem would not be solved. This is a statistical figure. We're not saying literally, like when we say 100% of elliptic curves satisfy Bsd, there's still the remaining 0% that we don't know the answer for. Okay, this is like a probabilistic computation. Okay. And so you might ask, well, what do we know about this other 0% of elliptic curves? It turns out these are the curves with rank larger than 1, and we know absolutely nothing about them. So even if we knew Bsd, statistically speaking, was true for 100% of elliptic curves, we would be quite far from resolving the Bsd conjecture. However, like I said earlier, the computational evidence, even for these curves of rank larger than 1, there is still computational evidence, and it's still overwhelmingly likely that Bsd is true. Okay, now the most important thing I have to say about this is not even the weak Bsd conjecture, because it turns out one of the directions of this if and only if is already solved, thanks to Wiles and his advisor Coates. So first of all, a quick definition. An elliptic curve over a number field K, a number field is just a finite extension of the rationals, has complex multiplication if its endomorphism ring, so self-homomorphism ring, is strictly larger than Z. That's fancy algebraic language. All that you really need to keep in mind is an elliptic curve with complex multiplication sort of has extra multiplicative structure on it, in the sense that there's an algebraic relationship between f of z and f of cz for any c in the number field, where f is the right-hand side of the elliptic curve. Don't stress about it. Complex multiplication means extra structure on the elliptic curve. So here's the theorem from Coates and Wiles. Let E be any elliptic curve over Q with complex multiplication. If E has infinitely many rational points, then L of E1 is 0. So what is that? That is one direction of what I called up here the weak Bsd conjecture, provided the elliptic curve has complex multiplication. This theorem is very hard, and I actually have not been through it yet. It is on my short list of things to go through, but we know it. And so you might say, well, hang on a second. Does that actually even apply to us? Do our congruent number elliptic curves have complex multiplication? If they do, then we get Coates-Wiles, right? We get one direction of this link in the chain verified to be true. And yes, it's very easy to show that our congruent number elliptic curves have complex multiplication. In fact, it's borderline easy enough that it's just an exercise. So En has complex multiplication for all n, and hence, if n is congruent, what do we know? If n is congruent, right? If and only if ENQ is infinite, but by this BSD conjecture link in the chain, we know that ENQ is infinite if and only if L of EN1 is 0, where only this direction is unknown, is unproven. So relies on weak Bsd. But this direction here is Coates-Wiles, and this is known, thanks to the fact that these guys have complex multiplication. So we have tied congruence to the L function of our elliptic curve, specifically its value at 1, whether or not it vanishes, which is huge. Unfortunately, while this is incredibly profound, it is still not checkable. It's certainly not easy to evaluate these L functions, especially their analytic continuations at 1 in general. So we have to keep going, but we're doing things. We're starting to get into this realm where we're going to be able to pull on modular forms, okay? So to summarize, suppose n is a square-free natural number. If it's congruent, then the L function of the congruent number elliptic curve attached to n is 0 when evaluated at 1. Assuming a weak version of the Bsd conjecture is true just for these En curves, then the converse is true. L of En1 equals 0 will imply n is congruent. For this reason, because this value 1 that we plug into the L function is kind of the important value, we call s equals 1 the critical value of the L function. You also saw above, this was the fixed point of the functional equation, and it lies in the middle of the critical strip of the functional equation as well, okay? So we're getting there, we're doing things. Now, again, whether or not the L function is 1 is still not an easily checkable condition. So we need to figure out exactly when this happens. And to do that, I want you all to wave goodbye to elliptic curves, because we're just not really going to see them too much more. I mean, we're going to, occasionally we'll bring them up and draw some parallels between what we're about to study and elliptic curves. But in general, we're saying goodbye. We've gotten all we need from them, okay? We're going to say goodbye to elliptic curves, and we're going to enter the world of modular forms. So I view what we're doing like this. If I had to draw a picture of what's going on, I sort of view it like this. You start with n is congruent here. And then you climb the elliptic curve hill. Okay. And the top of the elliptic curve hill is the L function. And then you have to climb back down the hill to get to the congruent number theorem. And climbing down the hill is the world of modular forms. Okay, so we want to fill in this blank using the theory of modular forms. N is congruent if and only if what checkable thing is true, right? So if you thought we were done simply because we've done some hard things, some hard theorems have come up, and we've reached the stage involving a millennium problem, then think again. We're roughly halfway to our goal. And while the rest of the proof of the congruent number theorem is resolved in the sense that it doesn't rely on any, conjectures or unproven theorems, that doesn't make it easy. There are quite a number of hard theorems still in our way, although they are known. So now we continue on into the vast world of modular forms, which are just really special holomorphic functions with nice symmetries. So I'm going to give you a crash course on modular forms and then some. I'm going to have to tell you quite a lot. There's lots of definitions and constructions and facts you need to be aware of, or else just the rest of the theorems that you need to prove the congruent number theorem just won't even make sense to you. So let's start off nice and easy here. GL2R. So if R is a ring, then GL2R is the group of 2x2 invertible matrices with coefficients in that ring. Okay? And SL2R is the subgroup of GL2R of those matrices that have determinant 1. We're also going to be denoting by this C hat the Riemann sphere, which is C union infinity. And another way of denoting that is, C union infinity is also the projective line. So I might write any one of these three things at any given moment, depending on how I'm feeling, and they all mean the same thing, the Riemann sphere. Okay, so let me take a matrix in SL2Z. So we're going to let our ring be Z now, the integers. So I'm taking a 2x2 matrix with integer entries, and it's got determinant 1. I'm going to call the entries A, B, C, D, right? I'm going to define an action of SL2Z on the Riemann sphere like this. So you give me a number in the Riemann sphere. I want to tell you what G times Z is, where G is this matrix. What it is it's AZ plus B over CZ plus D. You kind of make this rational function out of these coefficients where the numerator and the denominator are just linear functions. The coefficients match up perfectly. Okay. And then this is supposed to be an action on the Riemann sphere, so I have to tell you what is G of infinity, what is G times infinity. G times infinity, borrowing from calculus, I suppose, if you'd like, in limits, we're going to just define that to be A over C. You can think about taking a limit as Z goes to infinity here. These expressions here are called fractional linear transformations of the Riemann sphere. For obvious reasons, they are fractions of linear maps, right? So a couple exercises for you to try. If G is plus or minus the identity matrix, which certainly lives here, then those give the identity map. If I pick one of those to be my G value, then GZ is just Z. And as a matter of fact, you can also show no other matrix acts trivially like that. There's no other matrix G besides plus or minus the identity such that GZ is Z for all Z. In other words, if you want to say this in algebraic language, if we call capital gamma SL2Z, and then we call capital gamma bar gamma mod plus or minus I, so mod out by these trivial guys, then we would say the action of gamma bar on the Riemann sphere is faithful. Okay, that's just a different way of wording the exact same thing, right? Here's another exercise. If I restrict my attention to Z values in the upper half plane, okay, so what's the upper half plane? It's only the upper half complex plane, and I'm not including the real axis. So this is going to be my upper half plane H, and I don't want the real axis included. Okay. If you do that, if you make that restriction, then you can show that gamma which is SL2Z, takes H to H. In other words, gamma as a group of matrices acts on the upper half plane. You're never going to escape the upper half plane by acting on it with gamma. Okay. So these are both of these exercises are very easy. Now, gamma is the big boy, SL2Z, but SL2Z, it turns out, has a lot of subgroups that we care about as well. There are a number of them. The first ones that I'm going to define are these so-called gamma of capital N's, where in here I should say N is a natural number. What are these? These are the subgroup of SL2Z of matrices, which are the identity mod N. So what I mean is, it's this. So this is the set. Let's come over here. This is the set. Usually the way it's written is like this. It's the set of all 1, 0, 0, 1 mod N. But that's just shorthand, right? What does that actually mean? That means if you reduce the entries of your SL2 matrix mod N, you get the identity matrix. So for example, it's an easy check that gamma of 1 is just gamma. So you can convince yourself of that if you'd like. And these guys have a name. You can make one of these for any N that you want, and they're called the congruence subgroups of level N. That's actually not fully the precise definition. A congruent subgroup just needs to be something that contains one of these, or is contained in one of these, but these are really the only ones that we're going to be caring about, except for a couple other special subgroups that I'm going to talk about right now. Now, if you are a subgroup of level N, if you're a congruent subgroup of level N, I think we can all see probably immediately that you're also a congruent subgroup of level any multiple of N. Okay. So convince yourself of that if you don't believe me. That's not going to be a huge fact for us or anything, but it's just worth mentioning. And are these the only special subgroups of gamma? They are not. There are several others, but we're going to need two of them kind of immediately. We're going to have to define this so-called gamma not of N. And what that is, so this is gamma of N. Gamma not of N is the subgroup of SL2Z of matrices that look like star, 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 0 mod N. So what we're doing is we're just requiring that the lower left corner be 0 mod N, and we have no other restrictions that we're placing on this matrix. So that's going to be an important subgroup for us. And then there's one other one for now, and that's this gamma 1. And gamma 1 is got some more restrictions on it. Gamma 1 of N is the set of all matrices in SL2Z such that you're kind of almost the identity mod N. You got to be 0, you got to be 1 on the diagonal and 0 in the lower left corner, but then we don't care what happens in the upper right corner. Okay, so you can check these are all subgroups. Okay, they're all, of course, going to, I want to emphasize, I'm pulling these out as subgroups of SL2, right? Like this is not obviously an SL2. These are, but this one isn't, but I'm requiring that they also live in SL2Z. Okay. Okay, so we've got these nice subgroups out of the way, the congruent subgroups, and then this gamma naught and gamma 1. Here's another definition. Let's suppose I take 2 points in the upper half plane. I'm going to call them gamma equivalent if I can get to one of the points from the other by multiplying by an element of gamma, by multiplying by a matrix, by acting with a matrix in SL2Z. Okay. So I view it as like, just very simply, I view it as, so here's the upper half plane, right? Here's some Z1. If I act on Z1 with some member of SL2Z, we know we're going to end up in Z somewhere. Okay. If this second point Z2 happens to be gamma of Z1 for some gamma, then I'm going to call these two equivalent under this action, right? And then more generally, I'm going to call 2 points uppercase gamma equivalent if they are lowercase gamma equivalent for some matrix lowercase gamma and uppercase gamma. Okay. And then it becomes interesting, like, okay, are there regions of the upper half plane such that every point inside this region, or every point inside the upper half plane rather, is gamma equivalent to some point in this region? And it turns out there are, and they're called fundamental domains for gamma. So a fundamental domain is a closed region F of the upper half plane, such that every single point in the upper half plane can be kind of mapped into F, or into the interior, into F rather, with some member of capital gamma. You can always kind of act on points in the upper half plane by a matrix, and by choosing a suitably correct matrix, you'll end up inside F. But we want to impose one other restriction, right? We kind of want the smallest F in some sense where this is true. In other words, we don't want 2 points inside the interior of F to be gamma equivalent. That would be stupid in the sense that we could just shrink this region down if that happened to us. And so proposition 1, can I give you an example of such a fundamental domain for gamma? I can, and here's the picture. If you take the upper half plane, okay, and again, the real axis is not actually included, and then you draw the unit circle, okay, and then you look at the following 2 lines: real z equals -1/2 and real z equals 1/2. So look at those lines. I should probably just make them solid, actually. Okay, then this region is a fundamental domain for gamma, if you include the boundary, because remember, it has to be a closed region, right? So my claim is this is a fundamental region for gamma. And there are others, of course, but this is the main one because it's got nice symmetry about the y-axis. Okay, so we have this. This is a crucial thing to be aware of. So, well, okay, you might ask then, well, wait a minute. In the definition of fundamental domain, we only required that no 2 points in the interior of F be equivalent. But what about the boundary of F? When do we get gamma equivalence on the boundary of F? That's the next question, right? And in this, for gamma, for this nice fundamental domain for gamma, we have the answer, and it's completely nice. 2 distinct points on the boundary of this region F, and I'll draw this in a second, are gamma equivalent if and only if real z1 equals ±1/2 and z2 is z1 ±1. Or if z1 is on the unit circle and z2 is the negative inversion of z1. So that's mouthy, but it's very nice. I can draw it very nicely. What we're saying is points on the opposite side of the green lines are gamma equivalent. That's one thing that we're saying. And not only that, it was an if and only if, right? So all pairs of points on the opposite sides are capital gamma equivalent. And then what about this piece of the boundary down here? Let's see. These 2 points would be gamma equivalent. Points that are symmetric on the unit circle about the y-axis would be gamma equivalent. That's all that we're saying. Which means, I guess, that up here at I is just not really gamma equivalent to anything, right? But every other point is, it's gamma equivalent to the point kind of right across from itself, across the y-axis. So we have this, and this proposition makes you wonder something, right? Let's actually go back to this picture for a second. what matrix gets me from this black point to this black point here? The matrix is the translation by one matrix, right? Which is 1, what is it? 1, 1, 0, 1, right? If you act on Z by this matrix, what happens? You're going to get 1Z plus 1 over 0 plus 1. What does that do? Translates Z by 1. You end up at this black point over here. And then how about, so that governs this set of equivalences here. What about this set of equivalences here? How do I get from this point to this point? Well, I told you in the proposition, but I didn't write it as a matrix. To go from this black point to this black point, you're doing Z1 is being sent to negative 1 over Z1. It's negative inversion. We have a matrix for that as well, right? It's called S. And what is it? It would be 0. Well, there's two different ways you could write it. I think it's usually written like this, though. You could also put the negative here, but it doesn't matter, right? So this matrix will send what? It'll send Z to 0Z minus 1 over Z plus 0, which is negative 1 over Z. Okay, that governs these equivalences here. And it seems like those are the only two matrices that matter, right? As far as gamma equivalence is concerned. So you might wonder, well, to what extent is that true? And we get the next proposition. It turns out S and T generate gamma bar as a group. Remember, what is gamma bar? It's gamma mod plus or minus the identity matrix. So what that means is, I mean, what's that saying geometrically? It's saying if you've got some random point in the upper half plane, you can always act on it by powers of only S and T to end up inside this orange region or on the boundary somewhere. You don't need any other matrices other than powers of S and T to end up starting anywhere in the upper half plane you want to being inside this fundamental domain somewhere. And this is not totally clear, right? I mean, once you look at the proof, it kind of becomes a little more clear, but it's certainly initially, at least, a little bit surprising, at least in my opinion. Okay, so we're getting somewhere. We're getting these things. We're getting some stuff, good stuff out of the way here. Now we're going to do one more thing, right? Remember how when we were talking about lattices, what were the functions we were looking at on lattices? We were looking at elliptic functions, right? Elliptic functions are doubly periodic. So what that meant was on the lattice, we were looking at functions whose values on points that are just opposite each other in the fundamental parallelogram are the same. But what do you notice is happening here? It's almost like the same thing is happening, right? It's almost like things that are on opposite sides of this domain are the same somehow, just like with the lattice case. And so what are we motivated to do? Well, what did we do with lattices when we observed that? We turned them into tori by just identifying opposite sides, by gluing points such that elliptic functions took the same values on those points together. You can just do the same thing here, right? What you can do is you can take this region and you can identify these points that are gamma equivalent to each other topologically or algebraically, if you like. And what you end up with, I guess, I mean, it's kind of hard to envision the shape that you end up with if you identify gamma equivalent points up here, but it's some kind of weird funnel-y looking thing. So we're going to call that H mod gamma. It's the fundamental domain F with all pairs of gamma equivalent points identified. And like I said, I mean, I have a picture in my head of it, but I'm sure that whatever you're picturing is different. It's some kind of weird funnel thing, okay? And like I said here, this ought to remind you of how we made lattices before and built complex tori out of them. And this is no accident, okay? I mean, there's going to be deep parallels between the theory of modular forms and the theory of complex elliptic curves. That's what's going to happen. Now, what did we do? What did we have to do when we were working with lattices, though? we had to, what did we end up seeing? We saw that every complex torus was isomorphic as Riemann surfaces and group isomorphic to a projective elliptic curve, right? But only once we added a point at infinity to the elliptic curve, only once we projectivized the elliptic curve. So if we want to keep these parallels going that we're ending up with, we should add some kind of point at infinity or something to this H mod gamma. And that's exactly what we're going to do. We're going to define H bar to be the upper half plane with a point at infinity, but then we're also going to union the rationals. Because right now, the real line is not part of the upper half plane. We're going to union the rationals. And you might stop me right there. Wait, what are you doing? I thought you were just adding a point at infinity. Why are you adding the rationals too? Well, if you think about it for a second, you might be able to figure out why this is. These new points we added are called cusps. Okay, the point at infinity and all the rationals. And the reason for that is gamma permutes the cusps transitively. So you can always take the point at infinity and act on it, with gamma, and you'll never get anything else. You'll never end up anywhere except for at infinity itself or at one of the rational numbers. Conversely, if I start with a rational number and act on it with gamma, I won't end up anywhere but at another rational or at infinity. And what does this transitively mean? That means there's just one orbit here. Like you can get from any cusp to another cusp with some matrix in gamma. You can always get from one to any other one with some suitably chosen matrix in gamma. So that's why we add everything. We don't want to just add a point at infinity. If we do that and then we act on it, the thing is we're going to end up at points that aren't even in the domain of consideration here. So we're just going to add all the rationals in and fix that problem. And it's nice because, like I said, we only get one orbit for our action here. And show all this just as an exercise. Show all this. Nothing that I'm saying is hard to show here. And maybe I'll finish up. I'll get all the way to this definition here and then I'll stop. So I'll do these next 2 points. If you take a generic subgroup gamma prime of gamma, the thing is, it actually doesn't have to permute these cusps transitively. It might not be possible to get between all the different rational numbers just by matrices chosen in this subgroup of gamma. So when I say cusp of a subgroup, what I actually mean is a gamma prime class of cusps. Okay, all the cusps in the orbit, right? So all the cusps that can be gotten to by action via gamma prime. And so, for example, let me apply this language to the big group gamma. So for the full group, we would just say gamma has a single cusp at infinity. Why? Because remember, when I say cusp, I mean equivalence class of cusps under gamma. But we know that action is transitive. So all of the cusps are in one orbit. So I might as well just lump all these together under that one equivalence relation and call these guys one cusp at infinity. Okay. So when I say gamma has a single cusp at infinity, you can picture whatever you want geometrically, but this is what I mean precisely, right? And a little bit of motivation for next time. What we're going to be doing next time is we're going to be taking H union infinity, okay, and we're going to map it to the unit disk. And here's the map. We're going to send Z to this Q variable, which is going to be a very important variable for us. And Q is going to be e to the 2 pi I Z. And we're going to send infinity to 0. And you can check, this is probably something you even saw in your first complex analysis course. This is a continuous map, okay? And this is going to motivate our discussion for next time. The fact that this map is continuous and it will tell us nice information, all right? So I think that's good for today. As usual, feel free to unpause or type any question, unmute rather, sorry, or type any questions you might have in the chat. And I'm happy to answer them. Where is Cobalt? Thanks, Jim. Appreciate it. Hope to see you next time. I'm actually going to stop the recording here, but I will continue to take